Okay, this is the first little revision session on Introduction to Electric Fields. Quite a lot to cover, but as it's the first lesson, we're going to just mention some of the stuff as an introductory, and then we'll come back to them. So even though there are 5 things, we won't be going through them all in full detail. We're basically going to look at what is a field, how do objects become charged, electric field strength and electric potential, radial and uniform fields, and then we're going to finish up with a new formula, field between parallel plates. Okay, how can different materials be charged? This really is just some revision from GCSE. If we choose acetate, then basically if you rub a particular material, in this case acetate, with a cloth, then what happens is, if you remember from year 10, the electrons transfer from one of the materials to the other. In our case, the electrons are going from the acetate rod onto the cloth. So the cloth will become negatively charged, and the acetate rod would become positively charged because of the deficit of electrons on it. It's all about the movement of electrons. You've got to remember that from your previous studies. So what do I need to be happy with before you start this section of the course? Are objects usually charged or uncharged? Well, they're usually neutral, so they'd be uncharged. Yes, most things, in fact all things, have got hundreds of millions of electrons in them, but because they are balanced out by the protons in the nucleus, then overall the charge will be neutral. How do objects become charged? This friction's normally involved in this, and remember, it's a transfer of electrons. What happens to the electrons? Well, they are transferred between different materials. Like charges do what? I'm sure you don't have to remind yourself of this, but like charges will repel, and opposite charges will attract. And how can you charge a piece of polythene? Well, if you just look back at the little clip we've just seen, you could rub it with some kind of cloth. Okay, what's an electroscope? You might have seen these in lesson. It's quite important to know how they work, just in case you ever get questions set in the context. A gold leaf electroscope is used to detect charge. It's basically the whole thing's earthed, and then you've got a very small piece of metal. So the case will be earthed. You've got a small piece of metal connected to a plate at the top, and on this is a very, very thin piece of gold leaf. Now this gold leaf is only attached at the top, so it can move. So basically, if this plate becomes charged, then that charge will charge the gold leaf as well. And because of that, you're going to have the gold leaf will have the same charge as the fixed plate here. Because the gold leaf can move, then this will register a movement, and that scale here you'd be able to calibrate it and register how much charge, because the gold leaf would be repelled. So all you've got to do is, if you've got something that is charged, if you bring it near to the top plate, so if you've got something, say my mouse here is charged, as I move that close to the top plate, because of the excess electrons, say if it's negatively charged, if the excess electrons here, as you're bringing it close, those electrons would exert a force on the electrons on the metal plate, and they would move, and they would all find themselves being repelled down the metal bar. So the excess electrons would sort of all be down here, and because you've got excess electrons here and excess electrons on the gold leaf, then they would repel. If you touch the metal plate with something that's charged, so instead of bringing it near, if you touched it, then the same thing's going to happen. It will become charged. It will have the same charge as the object that's touched it. So if that was a negatively charged object, this would become negatively charged, lots of electrons on it, and those excess electrons will repel. So it's important to know how that works, because it does use some of the basic theory. Okay, so what are these things? These are electric field diagrams. It's important to know how these work. You've drawn some in lesson. You draw field lines around a charge, so there's some complicated ones, some simple ones. There's a mixture here. If you've just got a negative charge and a positive charge here, then notice that the field lines go from the positive to the negative. This is because the field lines show the direction of the force that a positive charge would experience. So if you plonk a positive charge in the middle here, it's going to be repelled from the positive and attracted to the negative. So it would move in the direction of the arrow. This is important because you've got to remember, electric fields you can attract as well as repel. If we put a negative charge here, then a negative charge would be repelled by this negative and attracted by the positive. So a negative charge would go in the opposite direction. Notice that the field lines never start or stop in empty space. These are continuing on. It's not as if the field stops here. They either start or stop on another charge, so you can see these stop on the negative charge, or they end up going to infinity effectively, so you'd show them going off in the diagram, which means that they're heading off towards infinity. No matter how far you go away, then theoretically you're going to still be in the electric field from a charge. Parallel plates have got an electric field between them. We'll look at those shortly, and this is a single plate with a point charge for positive. So get your head around these. It's quite useful because you will see diagrams in exam questions. A small point about them never crossing. If they ever did cross, if you think what that means, if you place a positive charge at the point where the field lines crossed, then that positive charge would experience a force in two directions, and the minute you've got a force in two directions from your mechanics knowledge, you would resolve that force into the true direction or the resultant force. So you never get field lines crossing. And the strength of the field, which we'll come to in a moment in terms of a formula, the strength of the field is indicated by how dense the field lines are. So in this particular field, there are more field lines around the charge in terms of density of field lines than there are here. So this means that the field is much more stronger around the charge itself. Okay, a little bit about electric potential and equipotential lines. We will come back to this, so this is just an introduction. The key thing here, if you move a charge in a field, then its potential energy is going to change. So here we have a field around a point charge. This is a positive. If I bring a positive charge in, so imagine if my mouse is a positive charge, then it's going to be repelled by the point charge here. So it would be difficult for me to bring it in. I would have to do work. I'd have to apply a force to bring that charge in. So I'm going to increase the potential energy of my positive charge as I bring it in towards this positive charge. The closer I get, the higher the potential energy. So we call these lines, these dotted lines, are lines of potential, or equipotentials. They're lines of equipotentials because they join up points of equal potential. So this circle here I'm tracing out would be at a particular potential, and potential is measured in volts, which again we'll come back to. But the main idea is that the potential energy within a field does change. We measure potential in terms of the amount of energy that a 1 coulomb of positive charge has got. So if I bring a negative charge in, then a negative charge is going to be attracted to this. A positive charge would be repelled. So they're going to have positive and negative potential energies. Equipotentials are points in a field that have the same electric potential, and they are always perpendicular to field lines. So you can see my field line here, they are always perpendicular to, and in this parallel plate, these are my field lines, the blue lines, and the equipotentials are always going to be perpendicular to. Any electrical conductor is an equipotential surface, so if you look here, all of this whole positive plate would be at the same electric potential, and all of this negative plate will be at the same electric potential. So our first formula, you might have seen if you've done gravitational fields, or you might remember this from work in year 10, that gravitational field strength is force per unit mass, so that's newtons per kilogram. That's how we'd measure that. Whereas our electric field strength is similar, but this time it's force per unit charge. So instead of being newtons per kilogram, it's newtons per coulomb. So a nice easy equation to start us off with. So applying the equation, if you imagine this is an electric field, we've got a point charge, a small test charge of x in that electric field. I can see the field lines are going this direction, they're going down the page. So I know that I've got a positive charge somewhere above the page that you can't see. So if x was positive, it's going to follow the lines of these, follow the direction of these field lines. A small test charge of 3.5 microcoulombs is placed at a point x and experiences a force of 70 millinewtons. What is the electric field strength at this point? If you just go F over Q, you can shove that in your calculator. You should have 20 times 10 to the 3. So a nice simple question to start you off. But more importantly, some notes. Electric field strength is a vector, so you will always have to consider direction. You might have to state direction. So in my case here, it would be downwards. If the test charge is positive, the force will be in the same direction as the electric field. So we'd say the point, this charge X would move down the page. If the test charge is negative, it's going to move up the page. It will go in the opposite direction as the electric field. Okay, quick note about radial and uniform fields. We will come back to these, but this is just an introduction. A radial field will be this. This is a radial field, and we'd say it's non-uniform. We'll come to that in a minute. And this is a uniform field between two parallel plates. The reason a radial field is called a non-uniform field is if you just look at the field lines, then you can see the field lines are not evenly spaced. So here, the field strength is less than here. In contrast, if you look at a uniform field, wherever you go between these parallel plates, the field lines are always evenly spaced. So this is a uniform field. The electric field strength is the same wherever you are, whereas the electric field strength here is not. Just looking at the two parallel plates field in a little bit more detail, there is a formula that we need to just mention about this. Notice field lines are parallel, they're at right angles to the plates, they go from positive to negative. That's all what we've covered. The field strength is the same everywhere because the blue lines or the field lines are evenly spaced. The potential of the field will vary. Obviously it varies, and the equipotentials, if we drew them in, they would be horizontal lines. If you think about that, if I've got a positive charge, as I move it closer to the positive field, its potential energy would increase. As I move it towards the negative plate, the potential energy would decrease. So the potential within this field is different. The field strength is the same, but the potential is different. Rather than using E equals F over Q, it'd be nice if we had a formula using the voltage between the plates and maybe the distance, and we derive this in lesson. It's ever so easy to derive, and we say that the field strength is equal to V over D, which is the voltage between the plates, the potential difference between the plates, and the distance between them. Think about the units then, just finally. We've got two formulas to describe electric field strength. This is the standard one, or the one that applies in all situations. It's the force per unit charge, newtons per coulomb. But if your field is between two parallel plates, then you can use E equals V over D. Now the units for field strength here would be volts per metre. So we've got an equivalence of volts per metre and newtons per coulomb. Most of the time, if you're talking about the field strength of a particular point in a field, you tend to stick with newtons per coulomb, but if you're talking about the field strength between two parallel plates, you would say volts per metre.